Good evening, friends. Welcome to Manthan once again. Today's topic for discussion is all about black holes, what black holes are, and what are the various features of the black holes. To define a black hole, it's a celestial object from which no one can escape, not even light. That is why it is called as black hole, because it looks black in the outer space. Now, we will also try and understand how black holes are created, the science of collapse and the core mass, how they decide how the black hole is formed. And then we will try and understand what the structure of the black hole is. And before understanding what it is, let us understand what it is not. And then we will study about the various areas of the black hole, like accretion disk, horizon, and mass. And then we will try and consider what would be the black hole mass be made up of, what is its constitution. We will try and propose a concept of monoatom. And then generally black holes are considered as, weighing those many sun masses. We do not differentiate between the mass, but we will try and see if in a black hole a mass can be differentiated. The mass of the black hole can be differentiated. Then generally it is said that the shape of the black hole is spherical. Manthan model will question it, contest it, and suggest another model other than sphere, and provide sound reasoning also as to why we say so. And then we know that black holes are not stationary objects, they do move in the galaxy or in the universe. So we will see what are their travel habits. How do they move around in the galaxy itself? And we will also show that possibly all these black holes, once they form, they have nothing but no other choice but to move to the center to meet the supermassive black hole at the center. And then we will try and address a few contradictions. Generally, it is said that galaxy cannot survive without a supermassive black hole at the center. The very existence of supermassive black hole, the galaxy itself is because of supermassive black hole. But we will try and prove that galaxy can survive a supermassive black hole. Even if it is not there, it can still survive. Then we will take a few theoretical conditions wherein we will try and show that classical model of universe does not, it fails to accept such kind of a model. But when it comes to spacity or Manthan model, we will be able to explain such kind of theoretical galaxies. So let us go to the first part of it, whereas how black holes are created. Black holes are created when a star dies. So every black hole that you see, it once was a star. So for us to understand how black hole takes shape or forms, we need to understand the life of a star. And every star has got a limited life time. Like our own sun has around 10 billion years of life. And now this star's age is defined by the science of collapse and the core mass, and we will study both of them. The science collapse in the sense the star is made up of a core and an outer mass, and this core is where there are nuclear reactions going on. These are basically fusion reactions, and these nuclear reactions are the ones which are generating tremendous pressure and temperature, and in a way they are generating an outward force, and this outward force acts as a balance for the star mass from the outer mass collapsing on itself. So there is a kind of an equilibrium which is maintained between the core and the outer mass. Now obviously for a fusion to happen you need fuel. So it all starts with a simple molecule of hydrogen as fuel. So as and when hydrogen is fused into helium, and then hydrogen gets used up, helium starts getting fused, and like that you move on the periodic table to higher molecular weights. And all these processes are exothermic in nature. They are releasing energy, and as long as that is happening, there is an equilibrium between the outer mass and the core. But moment you reach iron in the periodic table, the fusion to to achieve an iron core is not an exothermic reaction, it's an endothermic reaction. It consumes a lot of energy. It's an energy guzzler process. That is when the engine shuts down. That is when the core shuts down of the star and the star collapses. And when the star collapses, not that every star which collapses ends up as a black hole. There is a particular criteria which is defined by Chandrasekhar, the scientist. It's known as Chandrasekhar limit. If the core mass of the sun, of the star that is collapsing, if it is more than twice the sun's mass, then it turns into a black hole. Anything less, it could either be a neutron star or a dwarf star. A sun like ours ends up like a dwarf star, and majority of the stars that we see in the night sky, they end up as dwarf star, more than 90%. Less than 5% end up as neutron star, and only 0.1% of the stars that we see in the night sky end up as black hole. That's a very small percentage, but if you look at number of stars in our own Milky Way, around 100 billion, 1 in 1,000 would turn out into a black hole. That would be millions of black holes. That yields millions of black holes. So that is not a small number. Now let's go and check on the structure and the shape. Now, as I said, before we go and see what it is, what a black hole is, let us see what it is not. It is generally said that when the star collapses, it collapses to a point where all the mass is represented in a zero volume and in infinite density. When we say zero volume, which means that mass does not exist, which means all the mass that was there from the original parent star got converted into pure energy. That is the only way. And one thing for sure we should understand, black hole is not pure energy, it is just mass. Why do we say that? If it was a pure energy, it would not have attracted the masses the way a black hole does. So if you have a black hole and you have a star nearby, it gets shredded, it gets attracted. So for this to happen, the black hole has got to be a mass. It's a densely populated, densely packed mass, but for sure it is mass, and it is not pure energy. Energy is unitary in nature. It has the habit of dissipating. Its idea is to just dissipate itself. Entropy is increased, but the energy does not affect another blob of energy. It is also said that black hole is a tear in fabric of space-time, especially when you have huge mass concentrated in a very small space. It is said that it kind of tears the fabric of space-time. It does not. There is no tear, because if there was a tear, when the black hole moves, the space would have had any kind of effect. But as you see, space behaves as though nothing has happened to it. The black hole comes and moves, but the space remains as it is. It is not just small black holes. Even if it is, you consider a supermassive black hole, it may be stationary with respect to the galaxy, but when you consider the whole galaxy itself moving, even the supermassive black hole is also moving. So 2 million suns of weight in that position is moving, but it is not tearing any space. So it is not a tear in fabric of space-time. So now let us understand what are the various areas of black hole. So let us try to move from outside towards inside the black hole. So when you are outside the ring that I have shown as an outer ring, you are safe enough, in the sense you are far beyond the influence of black hole. You will not be sucked in, or in any case you would not be affected. But as soon as you come in this band, which I have shown as accretion disk, that is where the mass gets heated up. That is where you are coming into the influence region of the black hole's power. And that is where the mass gets heated and it gets lit up. And that is why we see in the accretion disk in our telescopes. And that is why in the accretion disk you have the mass being seen. But what happens in this inner ring, which is called as horizon? Once you cross this, There is no way of coming back. That is where it is called as horizon, is because nothing can escape the influence of a black hole, not even the light. As long as you are in the accretion disk, maybe you have a chance to spend energy and escape. But once you cross this horizon, whatever kind of energy that you use, you just can't escape, because you need to travel faster than speed of light. Nothing can travel faster than speed of light, and even speed cannot escape. And that is why you have a horizon. And once you cross the horizon towards the center of the black hole, you do not immediately encounter the mass itself. It is much, much farther away, which, as I have shown here at the center, that is where all the mass is accrued or is deposited. Now, coming to the constitution of the mass itself, generally the classical model of universe says that this black hole is 2 million sun, it's weighing as much as 2 million suns or 1 million suns or 100,000 suns. It does not make a difference differentiate between the type of mass that the black hole is made up of, which we will try and do now. So what exactly is this mass made up of? First, we will consider the mass, which is a native mass, the mass that is related to the parent star that collapsed into a black hole. So try and imagine you have a mass of the star, whatever be the type of element that the star is made up of, it is collapsed into a small area which would be under tremendous or infinite pressure and infinite temperature. At that stage, what would happen to that element that made up the star? Whatever it be, whether it is proton, neutron, electron, and quarks, they would cease to exist. In the sense, they would be shredded. But shredding says that it is moving out, but that doesn't happen so. The enormous energy of the collapse of the star's mass would pack it up into a blob of homogeneous mass. In the sense, this also is a mass which doesn't have, usually when we say a mass, it is an element, it has got a proton, neutron, electrons. There would not be any element like this. It is just pure mass which is going to be formed into a blob of homogeneous mass. This is what Manthan proposes. This is almost like a monoatom. The whole mass of the black hole itself, the one which is related to the star collapse, it acts like just one single atom. As though you have a periodic table, you have molecular weights going up to the last one. This one would be the grandfather of all those atoms. Just one atom and tightly packed mass. And then why we talk about the types of masses, basically just now we learned that for a black hole to form out of a star, you have to cross that Chandrasekhar limit, which is the core mass equivalent to around 2 suns. But we have seen supermassive black hole which weighs around 4 million suns. It's as heavy as 4 million suns. So where did all this mass come from? Agreed that it could have started from a higher or a bigger star. The 2 suns is the basic minimum. Anything beyond that, it becomes a black hole. But what could it be? How heavier could the sun or the star be? The supergiant star that we have come across in the universe is weighing not more than 300 suns. So you can imagine where 300 suns is and where 4 million suns is. So quite a bit of black hole's mass is acquired mass. So we differentiate it as native mass and acquired mass. Native mass is the one which is monoatom, which is packed, solidly packed, whereas acquired mass is the one which it has acquired through eating all these various stars, planets, and the gas material around it. It is like in a fruit you have a seed and a pulp. So pulp is that acquired mass and the seed is the one which is the native mass. And native mass has far more effect on pulling matters towards it rather than the pulp. The pulp, of course, it is also powerfully packed because it is going under immense pressure. But all that pulp is going and sitting on the native mass. And one thing that we should understand is there is a no entry board for this acquired mass. Of course, it goes and gets stuck on the native mass, but the native mass is so densely packed and it is a single atom, there is no way the acquired mass can enter the native mass. So when you take a cross section of the black hole, you will see the outer part, which is acquired mass, and the inner part, which is the native mass.